Namaskar and I welcome all of you to my YouTube channel. This is lecture number 6 on magnetic properties of solids. Today I am going to teach you LANGEVIN'S classical theory of paramagnetism. So without further delay, let's get started. First, we consider a paramagnetic gas that contains n number of atoms per unit volume. Okay? Next, we assume that all these atoms have same amount of magnetic dipole moment mu. We also assume that there is no interaction among the magnetic dipoles. We know that in absence of any external magnetic field, these atomic dipoles will be randomly oriented. But if we apply some external magnetic field, then these atomic dipoles will try to align along the field direction. However, the thermal energy at ordinary temperature will resist such type of alignment. So, in thermal equilibrium, these atomic dipoles will orient themselves at an angle theta with the applied field. Now, let me write these points. Let us consider a paramagnetic gas. Let us consider a paramagnetic gas containing n number of atoms per unit volume, each having a permanent magnetic dipole moment mu. ठीक है? The mutual interaction, between the dipoles are assumed to be negligible. In presence of external magnetic field B, these dipoles try to align themselves along the field direction. However, the thermal energy at ordinary temperature resist such type of alignment. So, in thermal equilibrium, the dipoles orient themselves by making an angle theta with the applied field direction. ठीक है? Suppose figure number 1 like this. Here I am showing only one atomic dipole. Okay? The potential energy of charged dipole in this position is given by E equal to minus mu dot B, which is equal to minus mu B cos theta. Now let me mention this point. The potential energy of charged dipole in this position is given by E equal to minus mu dot B, which is equal to minus mu B cos theta. Next, let us apply Maxwell-Boltzmann distribution law. And according to Maxwell-Boltzmann distribution law, the number of magnetic dipoles having this particular orientation is proportional to exponential of minus E divided by Kb into T, where Kb is the Boltzmann constant, T is the absolute temperature, and E is the potential energy of charged dipole. Next, apply the concept of statistical mechanics, and according to statistical mechanics, the number of dipoles lying within the solid angle d omega, that is the angle between theta and theta plus d theta, is given by dn directly proportional to exponential of minus E divided by kbt into d omega. We know that the value of solid angle d omega is given by twice pi into sin theta into d theta. Okay? Again, the value of E is minus mu b cos theta. After substituting the values of E and d omega here, we will get dn is equal to some constant k into exponential of mu b cos theta divided by kb into t into twice pi sin theta into d theta. Okay? So, in the previous section, we obtained the total number of magnetic dipoles lying within the solid angle d omega as dn is equal to k into exponential of mu b cos theta divided by kbt into twice pi sin theta into d theta. Here k is a constant. One important point is that all the magnetic dipoles will contribute a component of mu cos theta, which is parallel to the magnetic field to the magnetization, whereas the components perpendicular to the magnetic field, that means mu sin theta, will be cancelled out. Now let me write these points, where k is a constant. Each one of these dipoles contributes a component of magnetic moment mu cos theta to the magnetization, whereas the components perpendicular to the field direction cancel each other. So, total magnetization total magnetization is given by M is equal to N, total number of atoms per unit volume, into average contribution of magnetic dipole moment of one atom, that is mu into average value of cos theta. ठीक है, this term can be written as n into integration 0 to pi mu cos theta into dn divided by integration 0 to pi dn. Let us substitute the value of dn here, where the value of dn is given by this expression. ठीक है, so finally we will get n into mu integration 0 to pi cos theta into k into exponential of mu b cos theta divided by kbt into twice pi sin theta into d theta divided by integration 0 to pi k into exponential of mu b cos theta divided by kbt into twice pi sin theta d theta. So after simplification we obtain total magnetization as M is equal to n into mu integration 0 to pi cos theta into sin theta into exponential of mu b cos theta divided by kbt into d theta divided by integration 0 to pi sin theta into exponential of mu b cos theta divided by kbt into d theta. Suppose this is equation number 1. Now let us substitute x is equal to mu b divided by kbt and y is equal to cos theta, that means dy is equal to minus sin theta into d theta. Now let us substitute these values in equation number 1. So finally we will get total magnetization M as n into mu integration, when theta equal to 0 the value of y will be plus 1, and when theta equal to pi then value of y will be minus 1. So the upper limit will be plus 1 and so the lower limit will be plus 1 and upper limit will be minus 1. Okay? And this term will become y into e to the power xy into dy divided by integration plus 1 to minus 1 e to the power xy into dy. So after simplification we will get the total magnetization M as n into mu into cot hyperbolic x minus 1 by x. ठीक है, and this term is known as the Langevin function. So m will be equal to n into mu into Langevin function. Suppose this is equation number 2. Here Lx is equal to cot hyperbolic x minus 1 by x is known as the Langevin function. Now let us take one special case. Case number 1. When x is very less than 1, that is mu b is very less than cavity. In other words, when temperature is very high and strength of magnetic field is very low, that is for high temperature and low field strengths, this function Lx becomes x by 3. The Langevin function becomes x by 3, that is Lx equal to x by 3. We know that the value of x is mu b divided by cavity. So under this condition, the value of Lx will be mu b divided by 3 kBt. So therefore total magnetization becomes m equal to n into mu into Lx, whose value is mu b divided by 3 kBt. Again we know that the value of b is mu naught into h. ठीक है, so after substituting this value and after simplifying, we will get total magnetization m as n into mu square into mu naught into h divided by 3 kBt. ठीक है, so therefore the paramagnetic susceptibility, therefore the paramagnetic susceptibility will be xi is equal to m divided by h. So the value of m is this one. So after simplification, we will get paramagnetic susceptibility as n into mu square into mu naught divided by 3 kBt, and this term can be written as C divided by T, where C is equal to n mu square into mu naught divided by 3 kB, which is known as the Curie constant. ठीक है, where C equal to n mu square into mu naught divided by 3 kB, and this is known as the Curie constant. Curie constant. ठीक है. So this expression is known as the Curie law. ठीक है. So if we plot a graph between susceptibility and temperature for a paramagnetic material, then we will get this type of curve. ठीक है. Again, if we plot a graph between 1 by xi versus temperature, then we will get this type of curve, and the slope of this curve will be 1 by c. Let us discuss case number 2. ठीक है. When x is very greater than 1, that is mu b is very greater than cavity. In other words, strength of magnetic field is very high and temperature is very low. ठीक है. That is for high magnetic field strength and low temperature, the Langevin function becomes 1. The Langevin function becomes 1, that is Lx is equal to 1. So in this case the magnetization becomes total magnetization becomes M equal to N into mu into Lx. Here Lx is 1. So this is known as the saturation magnetization. ठीक है. MS, where MS is called as the saturation magnetization. That means in this case all the atomic dipoles will be aligned along the field direction. ठीक है. That is in this case all the dipoles will align along the field direction. ठीक है. So if we plot a graph between magnetization and this term, then we will get a curve like this. Here we have seen that if we increase the magnetic field strength, then the magnetization tending towards the MS value, which is known as the saturation magnetization. ठीक है. This is all about today's video and I hope that you have learned a lot from this video.